Welcome to Chapter 4 of The Good Earth for Kimono Bay Ojibwe Community College Geology class. Here we'll be discussing plate tectonics. In this chapter, we're going to talk about science, which is what we talk about a lot in this class, right? We're going to go in detail about continental drift, evidence for continental drift, such as what's on the seafloors, and then a bit about plate tectonics and plate boundaries. As with everything in this class and science in general, these conversations are much more robust than what I'll be doing here in this introductory chapter. If you'd like to know more about this stuff, feel free to comment down below or shoot me an email, talk to me in class, whatever works best for you. There's a whole huge world out there about plate tectonics beyond what I'm going to discuss here. So, terminology. Paradigm. You maybe have heard the term paradigm before. A paradigm is a generally accepted view of how some aspect of the world works. A paradigm shift happens when you change your accepted view. You change your paradigm from one to another. Example given here is, who brings you presents at Christmas? Growing up, you of course assume your parents are the ones doing it, but then when you get a little older, you realize, oh, Santa Claus is bringing me those presents. I better get down to the mall and say hi to him. This is a paradigm shift from a former belief to a current belief. Plate tectonics is a good example of a paradigm shift of how we view the Earth and how it works. And keynote here, we're going to talk about paradigm shifts because they are very long, drawn out things in science. Paradigms don't change overnight. Instead, they are challenged, reviewed, and then eventually came to be accepted. Let's talk about the Earth, right? Plate tectonics paradigm shift starts with the fact that the Earth is divided essentially into two major elevation zones. You have the ocean floor, which is very, very deep, and then you have land in the shallow ocean surrounding the land, which is obviously higher than the ocean floor. Two big differences in elevation. Oceans are deep, right? In the early 20th century, there were many pre-plate tectonic paradigms out there, many ideas of how the Earth exists and how you can explain some of these phenomena, such as, again, the elevation heights. One of them, for example, is the contracting Earth, the idea that the planet is cooling and contracting down as the heat that is given off sorry, let me restart that, please. The planet was formed, it was very hot. As that heat dissipated, the Earth contracted in. This contracting would cause the mountains to form, essentially wrinkles on the crust, right? And then as the Earth contracted in, sections of it would collapse under that contracting pressure, forming ocean basins, et cetera, et cetera. So you have a lot of vertical movement of crust. Well, there's some obvious problems with that. First of all, we don't see that vertical movement necessarily, at least to the extent of the ocean depth to the mountains. Secondly, the math doesn't work when you try to figure out about this contraction. Thirdly, mountains aren't wrinkles. And fourthly, evidence of heat being created inside the Earth that's not related to the formation of the Earth throws a huge wrench in this conversation, right? So Alfred Wegener came up with an alternative approach to this problem. Instead of the continents moving vertically up and down, for example, what if they moved horizontally north, south, east, and west, right? What if we, for example, said some 250 million years ago, the continents were in a different location? They could have been in a supercontinent called Pangaea and then have drifted apart over those 250 million years to their current location. In essence, this is an adaptation of a modern drawing, but Alfred Wegener's original drawings look kind of close to this. 250 million years ago, the Earth looked like this, with one giant continent and then one giant ocean. And then over time, everything started moving away from each other. You can see most things moving to the north. Australia and India are way down south. They're heading up towards the equator. Africa's rotating a little bit. North America is going to break off from Asia here. And you're going to get your modern situation, right? Why did Alfred Wegener think that the continents were in this orientation to begin with? He looked at many, many lines of evidence. For example, you can look at fossil evidence and notice interesting locations. Here we have 4 examples of fossilized creatures that do not exist anymore. And what he'd notice is that Cyanogathus in the top left there, that had fossils in Central South America and Central Africa. In only those two locations. So either this creature existed in two separate sections across the Atlantic Ocean, or maybe if I squish South America into Africa, the lines connect. Interesting. But when we squish South America and Africa together to connect the line for Cyanogaths, we also connect the line for Mesosaurus down to the bottom. And we also connect the line for Glossopteris. I'm sorry, I'm terrible with these words. This plant also connects all of these different fossil records, all connect when we squish these guys together. And then if we throw India, Antarctica, Australia in as well, we can puzzle piece together all these continents. And now we have nice seamless lines matching fossil records. We don't have to try to explain how a non-aquatic animal crossed the Atlantic Ocean have two separate populations if we don't have an ocean between them. But beyond that, we have interesting formations such as mountain belts. North America, the Appalachians, and I believe that's the Caledonias up at the top of Europe, are both mountain ranges that are very similar ages. And when we get to more about mountain building, you understand how to date mountains. But for right now, North America and top of Eurasia have very similar age mountain chains. And there's no mountains in between it, obviously, because that's the Atlantic Ocean. So if we squish North America and Eurasia together, we can connect this mountain chain, and it kind of makes more sense. And then we can also squish North America, Africa, and South America together, and things meld together like a very nice looking puzzle. Beyond mountain chains, we can also look at things such as, in general, rock sequences seem to have been continuous but broken apart by the Atlantic Ocean. If you squish them together in the same way that you would squish together for mountain chains and for fossil records, you can also reconnect rocks that are unique only to certain locations. Paleoclimates is another big one. Again, same song and dance here. You have evidence of glaciation. You have evidence of similar climates in very distinct different locations. Connect those together. Coal swamps, for example. If you connect the puzzle pieces together for any one of the examples we've given, it also fits together for other things. The way that the fossils fit together also explains rock formations and explains things such as coal sheets or glaciation. They all follow the same basic puzzle. That's what we're talking about here is, as I said already, the glaciers. You have evidence of glaciers in the bottom of India, all the way up to Central Africa, places that do not get cold enough for glaciers nowadays. Well, if we squish everything together like this, and you have a glacier down at the bottom there around Antarctica, suddenly it makes more sense. Suddenly glaciers exist where glaciers should exist. And you explain the fossils, and you explain the mountains, and you explain the rock records, and you explain the paleoclimates. All of these things come together. Cool. Alfred Wegener proposed this idea. Funny enough, it wasn't very popular when he first proposed it. He had a solution to a lot of different problems, but he didn't know how his solution worked. Wegener was considered an outsider among geologists, and his use of deductive reasoning was considered quite unusual at the time. I can solve a lot of problems by doing this thing, but I don't know how the thing works. Well, that's a bit of an issue, right? You not only need the how, but you need the why. He knew the continents fit together this way, but he couldn't explain why the continents would move from that original Pangea, where all the continents are squished together, to what we have nowadays. For example, suppose that the contracting Earth hypothesis came up with alternative explanations for some of Wegener's observations. For example, the fossil record. How do you explain the fossil record? Well, land bridges existed across the Atlantic Ocean, and animals could move across them, and that's the excuse, right? And Wegener couldn't necessarily disprove that. Likewise, they also didn't have a way for continents to drift around. Interesting. So After Wagner, what did we notice? In the decades that followed his research, key observations about the seafloor contributed to new understanding of Earth processes. For example, we measured the topography of the seafloor, its vertical change, right? Calculate the age of the seafloor. We learned more about how heat flows underneath the crust, and then we did studies of volcanoes and earthquakes. And all these things come together to produce a quite interesting result. For example, if we look at the Atlantic Ocean here, we notice that by and large, the ocean is very flat. But right in the center of the Atlantic Ocean, we have this elevated mountain range going all the way from the top of the Atlantic Ocean all the way to the bottom. And it almost seems like a seam in the center of the Atlantic Ocean. That's interesting, right? Yeah, both continents have continental shelves. This is the light blue right around the continents here. And those go into the abyssal plain, which I said is the general, just deep ocean section. But that ridge, that submarine mountain range in the center, which is full of volcanic activity, that's a bit unexpected, right? You wouldn't necessarily look for that in a contracting Earth hypothesis, for example. Iceland, as you may know from volcanic activity recently, is full of volcanoes, and Iceland happens to sit directly on that seam we were talking about a couple minutes ago. We can look at these ocean ridges and we can trace them kind of throughout the world. That's interesting. Ocean ridge systems occupy much of the seafloor in the ocean basins. What we can also map out when we do the topography is ocean trenches, places that are super, super, super deep. Marianas Trench, south of Japan, of course, would be your most famous example. And what we find is that ocean trenches, or these really deep cuts, exist, one, adjacent to continents, and two, are found commonly along island chains. And a lot of them in the Pacific, not a lot of them in the Atlantic, right? We have the Puerto Rico Trench and the Scotia Trench at the bottom, but the trenches are the Pacific and Indian Oceans, not really the Atlantic Ocean. Interesting. So let's take that, and let's also calculate ages for the material. When we go and we calculate the age of these rocks, I'll explain more about how to age date rocks in another section, but we did talk about that a bit with geologic time. We find that the mountain ridge system, for example, the center of the Atlantic Ocean, is the youngest of the rocks. Here you can see it's some 0 to 10 million years right at that seam. The further away you get from the center of the Atlantic Ocean out to the edges, the older the rock gets. And the mid-ocean ridge system that we can trace throughout all the oceans of the world is also where you find the youngest rock. And the ocean trenches is where you find the oldest rock, at least in the Pacific Ocean. Interesting. I wonder what is all this stuff connecting into? Heat flow is also a very interesting thing. When we measure the way that the heat under the crust and the mantle behaves, we notice that it is hottest, it's most active underneath these young oceanic ridges, these mountain ranges. Interesting. Volcanism ties in very nicely to this exact conversation, because we find most active volcanoes located around the Pacific Rim, the Ring of Fire, which happens to coincide very well with the trench systems. Look at the dots here. Look at the trench systems there. Very close correlation. And then, of course, heat flow plays somewhat into that as well, at least for the western side of the Americas. Earthquakes. Earthquakes really do a good job of following the Mid-Atlantic Ridge system. And they also do a very good job of being big around those trenches, being big around those volcanoes. A lot of energy going in there, right? But we can go further into this conversation. We can look at how deep an earthquake event is. You can have lots of shallow earthquakes, for example, as this picture shows here, at those trench areas, and lots of deep earthquakes at the areas where the volcanism occurs. There's a term here, Wadi Benhoff zones. I'm not going to go into charts and zones with you in this class necessarily. That's a deeper conversation to have. But you can correlate not only the location of the earthquake, but the depth of the earthquake with everything else we talked about prior. Oops, there we go. Here's a picture connecting a whole lot of these conversations. You have the magma there at the left side of the picture, represents the heat flow that we talked about before, that's combining, that is in good correlation with the mid-ocean ridge systems. And then we also seem to find earthquakes at trenches, and trenches are not at the same place as the heat zones necessarily. Trenches are along edges, whereas the mid-oceanic ridge systems are obviously in the middle of the oceans. And then we have earthquakes, high-level, shallow earthquakes at these trenches. The deeper the earthquakes get, the further away from that mid-ocean ridge system you have, and that's also where volcanoes are developing. So we're talking multiple different conversations about the way the Earth functions. We're doing it all simultaneously. Cool. So let's propose a hypothesis, seafloor spreading. The seafloor itself is pushing out. We observe, for example, ocean margins without trenches. These are where you have older seafloor and little or no volcanism and earthquakes. Where you have oceanic ridges, i.e. those mountain ranges, you have lots of heat flow, young rock, and uplifted seafloor. The seafloor is higher at the mid-oceanic ridge system because it's a mountain range, right, than it is in these ocean margins that don't have anything going on. And then if we find ocean margin with a trench, we have very old seafloors, but we do have volcanism and earthquakes. Coupled with that, deep earthquakes, not just earthquakes, but deep earthquakes. Harry Hess proposed the seafloor spreading hypothesis when they collected data about the seafloors that we described there during World War II. So we can take the seafloor spreading hypothesis. We have all these observations. Let's interpret something from them. These oceanic ridges I would talk about, these mountain ranges in the center, perhaps that heat flow corresponds with heat coming up through the mantle from the inner earth and coming out at these ridges. As it comes out of these ridges at the center, it's producing a lot of lava, producing a lot of magma underneath the earth, buckling up the earth as it's creating it. It's creating mountain ranges by pushing this out. When you push the mantle, when you push the magma out of these oceanic crusts, that force of the magma coming up is shoving the ocean apart. As you can see with those arrows, if you can imagine arrows coming up and then turning left and right here, pushing the oceans out. As the oceans push out, if they run into something that doesn't want to move, let's say a continent, the ocean will go underneath the continent. This is because oceanic crust is more dense. Again, that's something we'll get into a bit more later, but continental crust is very tall and very less dense. Oceanic crust is very short and very more dense. So oceanic crust subducts underneath continental crust, giving you an explanation for the volcanism, an explanation for the earthquakes, an explanation for how the plates move, an explanation for why the plates move. It also explains the differences in the age of the seafloors and the topography of the seafloors. Ocean trenches exist. Go back here. Ocean trenches exist where the ocean wants to push and the continent doesn't want to be pushed alongside it. You do not have trenches along America and North and South America's east coast because that's not having pushback from the continent. You do have it along the west coast because the continent is being pushed by the Atlantic Ocean and it's running into the ocean and the ocean is going below it. The ocean going below it causes that ocean to fall, which of course would cause earthquakes and cause volcanoes because as the crust gets deeper, it gets hot, it melts, it comes back up as magma. Observation, interpretation, useful. Let's go a step further here. Let's talk about the Earth's magnetic field because this is a real killer of that contracting Earth theory, right? Additional observations about the magnetic properties of seafloor rock support the seafloor spread hypothesis. We can also talk about the Earth that has a magnetic field. In case you're wondering, the Earth's magnetic field works similar to a generator in the sense I'm sure you remember in high school playing with a coil of wire and a magnet, right? So you take a coil of copper wire, right? You coil it up, make it in a big circle, and you make a real long string of that, and then you touch both ends to a ammeter or something that can measure a voltmeter, I guess would work. An omnimeter is by what you used in high school. And if you move the magnet through that coil of wire, as you're moving the magnet, you will induce an electrical current in the wire. This is how essentially electricity is made, right? When you have electricity, you also therefore have magnetism because the two are very much connected. So the inner part of the Earth works in very much the same way. You have a fluid inner rich outer core, so a fluid iron rich outer core that is rotating around a solid iron and nickel rich inner core. This rotation kind of perfectly mirrors that coil and magnet approach that we were talking earlier to create magnetic and electrical fields, thus creating a magnetic field inside the Earth. We generally describe it as bipolar, like a bar magnet, right? With a magnetic field about 11.5, 12 degrees off orientation from the rotational axis, as shown here. When you use a compass, you are reading the Earth's magnetic field. So this magnetic field is defined by its direction, of course, where it points, and also by its inclination, i.e., the closer you get to each pole, the more vertical the field is because it's coming either going in or coming out of the north and south magnetic poles. The further you are away, the flatter it gets, so much so that when you're at roughly the equator, you have very flat orientation. These arrows are very flat out here. And the more north and south you get, the steeper the orientation of magnetic field. When you played with iron particles in a magnet, again, back in high school, you notice this very same effect. So we can use this concept and we can essentially take a magnetic signature from a rock, look at its declination, where it's pointing, its direction, and its inclination, how steeply it's pointing vertically, and we can determine where it's located because rocks in, say, the Midwest of America have a very distinct declination and inclination. You can tell where the rock is based on essentially what the compass is doing. So if you go to an older rock, and you find that its declination and inclination, where the points and how steep the magnetic field points is different from the current location, that means that rock used to be in a different location. Likewise, another cool thing is said here, the Earth's polarity, essentially our north and south poles, have changed over time. The magnetic north pole is on our geographic south pole because the north pole is where the magnet energy comes out, and the south pole is where the magnetic energy goes in. So right now we are existing, it's called normal polarity because it's our polarity, where the magnetic north pole is in the geographic south pole. We do have rocks that show the exact opposite thing, however, and these things are called epochs and they switch all the time. Super cool. Again, if you want to know more about this, comment or send me an email, talk to me in class. A lot of cool stuff going on here. But these changes in the magnetic field are more evidence of the rocks moving and the way the rocks move. And the excellent part about this all is it's captured in the Atlantic Ocean very, very distinctly. So what we have here is, as we were talking about earlier, the magma's upwelling, it's creating new ocean from the Atlantic Ocean, pushing the Atlantic Ocean farther and farther apart. When it's doing that, the rocks at that center that are being formed are formed in their current magnetic environment. So when they solidify in the magnetic field that is present. As this continues to happen, if the magnetic field changes, the new rocks in the center will be, when they solidify, will capture the magnetic field of, well, the new magnetic field. So when we look at the Atlantic Ocean, we find a striping pattern of this magnetic field reversals over time. The Atlantic Ocean has reverse and normal orientation stripes as it aged through magnetic reversals. At the center, at the very center of the ridge axis of the mid-Atlantic Ocean ridge, it is the current magnetic field. You go out a couple 10 million years out in rock age, you get reverse magnetic field. Go out further, you get normal again. And this striping pattern is the entire Atlantic Ocean. Right there, that picture at the center here, it kind of looks like a banana, almost like a gray and white striped banana. I believe that's an actual picture of what I'm talking about, where those stripings indicate different polarities. That is evidence that the rocks are not only different ages, but that the rocks are moving and the Atlantic Ocean is spreading and the Atlantic Ocean is pushing out, because that's the only way you could get this swapping to occur. So, long story short, Alfred Wegener is right. The continents are drifting around. Super cool stuff. So, let's remember Earth's layers real quick, right? We talked about this a little bit in chapter 1. This is 3 main layers: a crust, which is what we're walking on now, sort of the skin of the apple, the mantle, which is the meat of the apple, and then the core, which is, the seeds and stuff like that at the very center of that. Those really sharp things that get caught in your teeth and you gotta pick them out, right? That's the core. So major features of Earth's surface, a result of the process, is just only a few hundred kilometers down in the top of the mantle. A lot of what goes on for this heat change and these the flow of that pushes the continents around, that happens at the very tip top mostly of the Earth. We generally categorize this crust, mantle, core more specifically in the lithosphere and the asthenosphere. Lithosphere is what we're walking on. That's the hard stuff underneath your feet. And the asthenosphere is the softer plastic fluid-like upper part of the mantle that the lithosphere floats on. Analogy I like to use, it's not a good analogy, but I always seem to use it, is the continents are like the elbow macaroni, and the asthenosphere is like the pot of boiling water. So as you get the water going, it's circulating that heat, right? Moving the water. The macaroni will float around on top of the pot. That's kind of what's going on with the Earth. Although instead of macaroni, it's continents. Instead of boiling water, it's fluid-like molten rock. Yeah, right. 1-to-1, fantastic analogy. I'm so good at this. So these plates move around, and what I'm showing you here with the plate tectonics is a very broad scale approach. There's a lot of plates that interwork and smash into each other all the time. There's not just these like 7 or 8 that I'm showing you here. Funny enough, the Vatican City rides on its own plate. I think that's cool. And as these plates run into each other, they cause all sorts of fun, interesting interactions. Actually, I'll point out here on the left there, you see those 3 little cartoons: transform, convergent, divergent, boundary. Those describe the broad ways in which plates interact. A convergent boundary is when 2 plates are driving into each other, like 2 cars crashing into each other. A divergent plate boundary is when cars are pulling away from each other, such as the Atlantic Ocean. A transform boundary is when things are moving like perpendicular to each other. One moves down, one moves up. Classic examples of these things, a transform plate boundary would be the San Andreas Fault. I think like California, I always get this wrong. I'm sorry if I'm mistaken. This California thing is like moving north, and North America is moving south or something like that. And that north-south motion, when we get to earthquakes, talk about this better, that north-south motion is called a transform plate boundary because the 2 are just scraping against each other and not interacting with each other. Whereas a convergent plate boundary, this happens when plates run into each other. This is what's happening in the Cascadias in Washington, Oregon, British Columbia area, where North America is running directly into the Pacific Ocean, creating mountains, right? Mount St. Helens, Mount Hood, stuff like that. And as I said, divergent plate boundary, that is plates separating from each other. That is Atlantic Ocean. These cartoons are always cool because they cover a lot of what we're talking about here. Here we have at the center, the magma is coming up in a divergent plate boundary. And then as the ocean runs into that continent on the right, there was the volcanoes. That's a convergent plate boundary because they're running into each other. Melting rock. So all this stuff is going down. All this exciting stuff is happening. That's causing a bunch of recycling of the material of the planet. Right here, you can see the ocean is subducting down, melting in magma at the bottom. So when this stuff happens, you get a lot of heat involved, you melt rocks. The melting of the rocks produces magma, which is associated with the formation of the lithosphere at Oceanic Ridges and the generation of volcanoes near Oceanic Trenches. The rock melts for a variety of different reasons. The biggest of those, of course, being increase in temperature. But you can, funny enough, melt rock by decreasing pressure. If you remember, PV equals nRT. I think it's like Boyle's law of chemistry. I can't remember the name. And then the more water you have, the more likely you are to melt something. Here's a chart here showing that temperature pressure relationship there. Essentially, if you increase temperature or decrease pressure, you affect the melting point of a rock, thereby more likely to turn it into magma, or at least turning it into a fluid-like substance. The melted rock in the asthenosphere that gives it kind of a fluid nature to it has a lot less pressure on it than the rock directly below, which is solid, but a lot more temperature than rock directly above it, which is, again, solid lithosphere. So you get this cool partial melt of the rocks, which allows the heat to actually flow through and move the lithosphere on top, right? The X moving left, right, up, down to show how you can melt material based on those things. And then the more water it has, the more likely it is to melt. So yeah, all of these things, right? Everything I'm talking about, hugely more complicated than this initial conversation, of course. So let's talk about plate tectonic cycle. At Oceanic Ridges, and something we've discussed a lot, I'm going to solidify the concept, there we go, here. At Oceanic Ridges, new oceanic lithosphere is added along edges of two plates that are moving away from each other. That's what we're talking about with the Atlantic Ocean spreading, and the volcanoes in the center pumping out magma. As it cools, it creates, right, new ocean crust. That's what's going on here in the center. As these push away, it's being replaced by new stuff. When we look at the magnetic striping, that magnetic striping is the result of new ocean being formed. When this happens, the ocean runs into something eventually. It runs into continent. And this continental lithosphere hits at this, I think I said it before, a subduction zone occurs when, convergent, there we go. A convergent zone happens when two plates run into each other. If you have a plate such as a continental plate, those are lighter in general, they're less dense, I should say, and they're very tall. And then you have oceanic plate, which is shorter, as shown in this picture, and very dense. So when you have something, it kind of be akin to like your hand being flat, and your hand being a fist. And when those two, if you push them towards each other, when they run into each other, the hand that's flat is going to go underneath the hand that's a fist because, well, it's flatter, it's heavier, it's going to flow down. And as the fist rise up to the top, that's the continent, which is being uplifted by this result. The connection between the ocean and the continent forms what's known as a subduction zone. It's being subducted, being drawn down. And where these happen, you tend to get those oceanic trenches that we talked about at the start of this conversation. So this process results in older oceanic lithosphere being destroyed as it's subducted underneath continents, and then new material forming in the center of oceans. When this happens, as I said before, you get volcanoes, you get earthquakes. We'll talk about those things in the subsequent chapters. You can measure how fast the oceans move via many ways. The classic way, of course, is to measure hotspots. A hotspot is what happens when you have that oceanic, that magmatic material coming up like in the Atlantic Ridge, but coming up in the center of a plate rather than on the edge of a plate. So Hawaii is actually itself over the top of a hotspot, a location wherein sort of a pimple in the center of a plate is happening, and then magma is just popping up through the center. And the cool thing about Hawaii is, this doesn't have the picture I was looking for. Okay. The cool thing about Hawaii is that island chain actually is tracking the movement of the Pacific Ocean over time, because the hotspot is in a location below the lithosphere. The hotspot is in a location in the asthenosphere. And as the lithosphere rides over top of it, so analogy you can do at home, put your right hand in a thumbs up position and then move your left hand, float your left hand over the top of it. Your left hand is the Pacific Ocean and your thumb is the hot spot bubbling up. And you can actually trace the Hawaiian Islands all the way up, connecting almost to Russia and Alaska. There's an island chain, and all those older islands are underwater because they're so old, the oceans eroded them away. And the biggest of the Hawaiian Islands is also the newest, Hawaii. And new Hawaiian Islands are actually being formed right now at the present hotspot location, as shown by that star. Yep, so this is the motion. If we track how far away the Hawaiian Islands are based on how old they are, we can figure out how fast the Pacific plate has been moving over that set amount of time. So it's moved an average of about 12 centimeters a year for the past 5 million years, because the oldest Hawaiian island that's still standing right up there, I'm not even going to try to pronounce it, the one that starts with a K up in the top there, about 5 million years old, and it's about 600 kilometers away from the current location. We can take that idea and we can use that principle along with other various things. Actually, nowadays, we can just GPS track all of this to figure out how fast plates are moving and where they're moving. We have very, very fast plates, such as the Nazca plates and the Pacific plate, moving anywhere, again, 12 to 15 centimeters per year. We have very slow moving plates like the Antarctic plate, the North American plate, which are moving, 2 to 3 centimeters per year. And when you look, and when all this stuff happens, all these collisions go on throughout the world, that creates the robust geology that we have and recycles, again, everything that we're talking about. And I'm also going to, again, mention within all these big plates, there's little micro plates that are moving and engaging in their own separate little battles. So there isn't like 8 or 9 plates. There's like just tons of them. Here again, we're going over a somewhat still contentious issue of where's energy coming from. So we have, as we've been talking about a lot of the mechanism, the engine of plate tectonics is the motion of the heat, right? It is the energy from the center of the earth coming up and escaping out, right? It escapes out through volcanoes, earthquakes, stuff like that. But how deep is that energy actually coming from, and where are those convection cells, the rotation of that fluid-like mantle, where is that convection coming from? Here we have examples of okay. It's not going as deep as I thought it was. Sorry. Here we have examples of where the volcano is coming from. Is magma super deep, such as like down at the bottom of the mantle, or is magma up top near the top of the mantle? Open question. Very interesting. We don't really know, sadly. But there's a lot of fun conversation to be had about how deep magma is and how, like, where the origination of the molten rock at, say, the Atlantic Ocean actually comes from. So, I talked about this already. Divergent, convergent plate boundaries. These are when plates come together or fall apart, transform, move left to right. When we get into earthquakes, I think it's the next chapter, actually, I'll cover is earthquakes. When we get into that, we'll dive deeper into this conversation. Divergent plate boundaries, I've been discussing a lot the Atlantic Ocean. These images here kind of show how the Atlantic Ocean can form. And funny enough, Africa, the Horn of Africa, also has a divergent plate boundary cutting through it. So you're actually watching Africa be split in half into an ocean right now. But so remember, Pangea was once connected. Africa and South America were connected. North America and Europe were connected, right? There's all one continuous section of land. As the plates started to spread apart, when they spread, you had a valley forming in the breaking up of that plate. As it continues to spread, it gets deep enough that it becomes infilled with water. And once it becomes large enough, it turns into an ocean, right? So you can imagine over time, again, South America and Africa, because that's probably the easiest one to visualize connected together. As they started, they were one continuous landmass. Then a small lake formed between them, then a small sea formed between them, then the Atlantic Ocean formed between them over time. The convergent plate boundary is when two plates meet together. And there's actually many ways that this can happen. They all produce similar but unique environments. The one picture shown here is when two ocean plates meet. An example of this would be the Aleutian Island chain up south of Alaska. That is the Pacific Ocean is moving north, and the Arctic Ocean plate is kind of stationary-esque. So when those two hit each other, one of them has to be subducted down. I think the Pacific Ocean is the one being subducted down. And then when that happens, the ocean is subducted down, it melts the ocean down there and it creates magma. The magma rises up, creating volcanoes. The Aleutian Island chain at the bottom of Alaska is one such. Do we have a picture? Is an example of volcanic islands. It's a volcanic arc, is what we call it. And all the Aleutian Islands are highly active volcanism because that is the result of the Pacific Ocean being subducted down. If you have an ocean connecting with a continent, say in this example, the Nazca Plate running into South America, that's where you get your Andes mountain ranges. Same conversation, but instead of an ocean island arc, you get a mountain range forming on a continent. And that two continents run into each other, you get a mountain range. This is the Himalayan mountain range in Asia. Indian subcontinent smashed into the bottom of Asia some 65 million years ago and started buckling up the Himalayan mountain range. But I will notice here the Himalayan mountains are not associated with volcanism because these two mountain ranges are more bunching into each other than one obviously subducting down because they're both very light. So you get this crumpling effect more so than an ocean connecting with a continent where one is subducted down very much vertically and melts. And as I said before, we notice the crustal thickness respects what we just talked about. You have very thick crust where you have oceans and continents or continents and continents meeting. Again, notice the Himalayas there, that's 70 in Asia, or the Andes mountain range along the western part of South America, and then lots of thinner continents where you don't have these interactions as severe. This is the transformed plate boundaries that we talked about before. Again, yep, I was right, San Andreas. Again, this is kind of what happens. Almost had it right, yeah. So South America is moving south and Mexico is moving north. That's what it was. I always get that one wrong. I apologize. So this is when you have perpendicular motion more so than parallel motion. Things aren't going to run into each other. Things are going to run by each other. And truth be told, these three examples are almost always interacting with one another. You don't simply have direct headbutting of continents. They're usually moving at oblique angles to each other. So everything's a combination of transform. Everything is usually a combination of transform and convergent, or transform and divergent, because the Earth isn't as nice as these cartoons that we present here. And there you go. That was a lot, right? That is plate tectonics sort of in a short conversation. Thanks for listening. Check your Moodle, check your email, whatever software we're using when you take this, watch this video for more information on any homework I happen to do. Feel free to comment below anything that you find interesting or any questions you have. Shoot me an email, talk to me in class. And thanks for watching.